Okay, let's kick things off. Thanks for joining. So today, this evening, we are going to cover Learning Unit 7, which is sampling distributions. So last week, I emphasized that it's really important that you have an understanding of the normal distribution, because that's going to carry over to this learning unit and the next one. Okay, so I'm really hoping that you understand that. You went over the recording and you have a good understanding of it, because this is an extension of that. All right, so let me share my whiteboard to kind of talk you through what Learning Unit 7 is about. Okay, but as usual, just shout if you have any questions. Let me share my screen. Just give me a second. Okay. All right, if you can't see my screen, please let me know. All right, put my whiteboard on the left, and I'll talk you through the notes on the right. Okay, so before you look at the notes, let me kind of give you an idea of how the sampling distribution works. So let's say you're in a factory that manufactures tires, okay? And in the circle is basically everything in the factory, right? So we've got tires that are being made. So each X is a tire that it makes, okay? Okay, let me use circles. It's going to get confusing. So I'll use circles or my drawing of circles anyway. All right, so all of these are tires. And let's say each of these tires have a lifespan, okay? So it lasts for a certain lifetime. Now, from last week, we said that we can let a random variable represent something that we're trying to measure. So for these tires, let's say we're interested in measuring the lifespan of these tires. And the lifespan of these tires will represent by X. So that's why I use circles. I didn't want to confuse you. So X is the lifespan of a tire. All right. And let's say we're told that the lifespan of these tires follows a normal distribution. And that's very important, because if they tell us it does follow a normal distribution, then that means we can convert that X to a Z, like how we did last week, right? By subtracting the mean, dividing by the standard deviation. And then we can use the table in the back of our book to work out those probabilities, okay? So that's the handy property of a normal distribution. All right, so if we took any tire, right, if I was the quality control inspector, and let's say I took this tire here, I took it, this one, okay, and I'm going to assess what the probabilities of this tire, or any tire that I chose at random, right, but one tire. If I chose one tire and I want to work out what is the probability of any of these tires having a lifespan of above 25,000 Ks. So that means I would need to work out what is the probability that X is greater than 25,000. Okay, because I want to determine what is the probability that the lifespan of any of these tires is above 25,000 Ks. All right. So now I'm going to draw your attention to, on the right, okay, the information that's given to us is that they tell us that in this factory, the mean that this factory claims is 25,000, right? And the standard deviation, your sigma, is 2,500. Okay, so these are given to you, right? In general, you don't work these out, they are given to you, okay? Because these are the population values. They will be given to you, and you just need to use them in the equation. So that's our mu, right, which we'd have to use here. And that's our sigma, which we'd have to use there. All right, so the question wants us to work out what is the probability of a single tire having a lifespan above 25,500. So, okay, so it's going to change one thing. It's not a big thing. I just want to change here. The question was for the lifespan being about 25,500. Okay, so that's what we're being asked to solve mathematically. So let me just check the chat if there's any question. They're all good. All right. Okay, so to solve this, we are going to use what we did last week. Okay, we need to convert that x to a z. So let me sketch the diagram of what we're trying to solve. All right, we're trying to look at the normal distribution, which is a bell-shaped curve like that. Okay, the mean for the mu where it's centered is 25,000. And we want to work out the probability. So 25,500 will be on the right of it because it's bigger than 25,000. We want to work out what is the probability that x is greater than 25,500. So that means we need to work out this area here, everything on the right of 25,500, right? So this is our lifespan of the tire, which is represented by x. So in order to solve that, we need to convert it to the equivalent z variable. So we got the same type of graph, but now it's in terms of z, which is centered at 0, all right? And the equivalent z value for 25,500 is determined by working this out. So in other words, we will plug our values in. So z equals x, which is 25,500, minus the mean, which is mu. So all I'm doing is I'm following this equation here in the block, right? So I'm going to plug in mu, which is 25,000, and divided by sigma, which is 2,500. Okay, so these values here I'm plugging in. If you work that out, you get a value of, still quickly, if it's 0.2. Okay, it's 0.2. All right, so that's the z value here. The equivalent z value is 0.2. Then you use the table in the back of your book and you work this probability out. Okay, this is what we did last week. Okay, so this is everything that's said so far. This is what we did last week. It's just a recap of what we covered last week. And if you work out this area, you'll get a value of 42.07%. So the answer for this question is equal to 42.07%. Okay, nothing new. This is what we did last week. All right. Okay. Back to the chat. Okay, so far so good. Okay, so what we've answered here is question 1.2. This is problem one, sorry, problem one here. We've solved this. This is the individual lifespan. In other words, we're just looking at an individual tire. Okay, to look at an individual tire, we would use the approach we did last week. But now things are a bit different. For this learning unit, we may not be interested in looking at just one tire. So what I mean by that is, let's say now, let me go to another page. Now we have a sample. So you're the quality inspector, you go into this factory and you collect 40 tires. Okay, so altogether there's 40 of these circles here. Okay, so this is your sample. You're only looking at a sample of the tires in the factory, and your sample size is represented by the letter N, which is 40. Okay, so you're the quality control inspector and you sample 40 tires at random. Okay, but now instead of looking at an individual tire, the question is, based on the sample, there's an average for the sample. Okay, so if you look at all 40 tires, and if you add up their lifespan and divide it by 40, you'll get an average. That's the sample average. So the sample average, or the sample mean, same thing, is represented by x bar. And the question here is, what is the probability that the sample mean, in other words, X bar, is greater than 25,500? 25,500. Okay, so this is what we're being asked now. In the previous page, we were asked to find the probability of X greater than 25,500. But now it's X bar. So we're not doing this. This is what we did before. Now we're doing this. And it's a big difference in how you solve these two. All right. You would be interested now in the average of the sample, right? You're trying to work with probabilities in terms of this sample average. Now, how you do this is the only difference between what we did before is how you convert X bar to Z. So previously, we used this formula. We use this formula to get the Z. We use Z equals X minus mu all over sigma. That's what we did before and last week. Now, for the X bar, we are going to use a different formula. We're going to use this formula. Z equals X bar minus mu all over sigma divided by square root of n. You don't need to memorize this formula. It's given to you in your formula sheet. You just need to make sure you understand the difference of what probability you're trying to work out. In this case, you're asked to work at the probability of the sample mean being above 25,500. So you would use this formula. All right. So everything remains the same as what we did in the previous question. Your mu doesn't change. Your mu is still 25,000. Your sigma is still the same, 2,500. And now you have this additional n in the formula. And that's your sample size, which is 40, which is given. So now the only difference is how you convert it to a Z. So if we're going to convert this to a Z, all right, it's going to be 25,500. So remember, we're using this formula now. So for your X bar, you are using this value. Okay, so it's going to be 25,500 minus your mu, which is this. And the denominator is different. It's sigma, right, which is 2,500 divided by the square root of 40. That's how you get your Z value now. That's the difference. And if you work that out, you get a value of 1.26. 1.26. So in other words, you need to work out the probability that Z is greater than 1.26 instead. So if I draw this graph, okay, your Z is here, 1.26 is here, and you work out the probability of Z greater than that. So you have to work out this area here. And this just follows from last week. It's exactly the same as how we did last week. All right. You go to your table and you work out this probability. You'll get this value from the table. And this value here is 10.38%. Okay, so the difference here is how you convert your X bar to Z. That's the difference between what we did now and last week. Okay. Okay, are there any questions here on this so far before I move on? So just in other words, the first question, if you have a question.
Hi, sir.
Yes.
In the exam, will they always give you the standard deviation and the mean?
Yes.
Okay.
Yeah.
That's all I wanted to know. Thank you.
Okay, no problem. Yeah, so don't stress about that. Okay, so the difference is, well, the takeaway here, right, and the real world kind of application here is this graph will kind of summarize it. All right, so don't worry about the writing in it, just focus on the color for now. All right, the blue line is the distribution you will use for an individual tire. Okay, now for an individual tire, it has a very spread out distribution. But as you take a sample instead of looking at just one tire, when you look at a bunch of tires collectively, then the distribution of the average for that sample changes. It becomes a lot narrower, and that's the green line. The green line is the distribution for X bar, right? What we did now, your X bar, which is this here, that's the green line. That follows the green line distribution. But if you're looking at X, a single tire, then it follows the blue line. So often in practice, when we do quality testing, we take a sample, because what the spread means, right? When you see a spread like this in its distribution, the more spread out, the more uncertainty there is, okay? Because your values can vary widely. You can go from one extreme to another extreme, all right? But as your distribution narrows, then the uncertainty becomes less. And that's essentially what you're doing when you take a sample. When you take a sample, then you get a more reliable result, right? A value that's not as spread out, because you're looking at things collectively. And maybe think of it as this way. It might be not the greatest example, but if you look at maybe a class of students, right? So if you have if you look at an entire class of students that write some, say, math exam, if you were interested in determining what's the chance of the average of that class being above 60%, you would get a more reliable result if you took the average of the class and you were trying to work out that probability versus you trying to work the probability of any student at random exceeding that mark. Okay.
Hi, Daryl. I have a question. I'm a bit confused on how we got 10.38%. I'm looking here at the table and I am not following.
Okay, let's do it together. All right, so we have this table here and 1.26 is here, okay, on this graph. So we want to work at this blue area. So what the table gives us instead is it gives us this area here in green that I'm shading, because the table gives you the area from 0 to that 1.26. So let's look at the table and I'll just drag it across. All right, so we're looking, our Z value is 1.26. So 1.2 is here. 1.26 is, if I go across, it's this column here. So we get a value of 0.3962. So this green area, oops, is 0.3962. So it might not be the exact value. Let's just check, right? So this green area is 0.3962. Then the blue area is just the remaining area of 50%. So if you want this value, it's going to be 50% minus this value here, which is 39.62%. What does it give you? Check my calculator. Maybe someone else can do it faster than me. Oops, 0.5 minus 0.3. 10.38. Danae, does that make sense?
Yes, it does. Thank you.
No problem. Okay. Okay. All right. So far, what we've been doing is we did a quick recap of what we covered last week. right, for variables that follow a normal distribution. And specifically, we're looking at the average of something being above something or below something. Then we looked at the sample mean. Okay, so if you took a sample, we'll be interested in looking at what is the probability of the average of the sample being greater than something. So we've only looked at averages or means so far, right? But you can also get asked about proportions. Now, proportions are percentages instead. So for instance, remember, like if you were interested in what percentage of people in Santon smoke, that isn't an average. You would get a percent, right? That's proportions, right? You get a percent. Let me move this table across. And when you work out, when you're dealing with proportions, then how you get to your Z value is a bit different. All right, so let's look at an example, kind of talk you through what I'm saying. So this question, right, a factory on the top, on the right, a factory has a historical defect rate of 5%. So whatever they're manufacturing, they have a default rate of 5%, right? So of all the products they create, 5% of them are defective, right? So as a quality control inspector, they take a random sample of 100 of these components, right? So yeah, you take 100 components. So I'm not going to draw 100 circles, but you get the idea. So in this basket, there's 100 of these components, right? So your sample size is 100, okay? And the question is, what is the probability that the inspector finds a sample proportion, right? So the keyword is proportion. So it's not averages, it's proportion. So what number out of the 100, right, would be defective? So what they're asking is, what is the probability that the sample proportion, P, is greater than 10%? Sometimes they drop the hat, okay? They just leave it as P, it's okay. But either way, just know it's both the same thing. Right? So what is the probability that the percentage of defective components from this basket here that you've selected is more than 10%? So what you need to just take away from this, right? You don't need to prove this result. You just need to know how to use this result. When you deal with proportions, now to convert this to a Z, you use this formula here. P equals P minus pi all over square root pi into 1 minus pi. The formula is, you don't have to memorize it. It is given to you, all divided by n. So everything in the denominator falls under the square root sign. Okay, this is the formula you use to convert, I'm sorry, not P, I'm confusing you. Not P, it's Z. So to get Z, you use this formula here when you're dealing with proportions. Okay, so that's the difference from what you did before to now. It's just a different formula to get your Z, right, when you're dealing with proportions. Now, pi, right, this pi here, this is the symbol for true proportion. You would have did this in learning unit 1 for statistical terminology. But if you don't remember, don't worry, I'm just refreshing your memory here. So the true population parameter, right? So remember, you took a sample, all right? But the true value for the entire population is 5%. So that's what your pi is. Your pi is 5%. All right? Your n, we already have that. That's a sample size, which is 100. And then for p, all you're going to do is plug in this value for p. You have all the values to feed into this equation in the block, right? So if we want to work out the z value is p, which is 10%, minus pi, which is 5%, divided by square root pi, which is 5%, into 1 minus 5%, all over n, which is 100. Okay, you plug all of that in, you work out the z value, and I get a z value of, you get 2.29. We get a value of 2.29. Oops, what's happening there? 2.29. So remember, for this, what we're trying to solve, I have to draw it. Okay, this is your proportions, which is centered at the true proportion value, and this is your p-values along the axis. So what you're trying to solve is, you're looking at where there's 10% on this axis from this value here, 10%, and you looking at what is the probability of p greater than 10%. So that means everything on the right greater than 10%. So this blue area here. There you go. You're trying to work out that area there. That's the area you're trying to figure out. And if you figure that out, that's the answer. So what you've essentially done by getting the z value is you've mapped the equivalent p-value to the z value. So here, this 10% is equivalent to 2.29 for your z distribution. So you need to find this area here, just like what we did earlier. Okay, you go to the back of your table and you want to work out this area here where z is 2.29. And if you do that, then you'll see from the back from your table, this area will be now 0.0, so about 1.1%. 1.1%. Or if you're going to leave it as decimals, it's 0.011. That's your answer. So that's the answer for this question. So there's a 1.1% chance that the number of components from your sample, there's a 1.1% chance that more than 10% of your sample is defective. Okay, so the takeaway here is, when you're dealing with proportions, you use this formula to get the z value. And as soon as you have the z value, then you use the table in the back of your book, just like what we did last week, to find the probability. Okay, any questions? So that is sampling distributions. Like I said, I did say it's so important that you understand the normal distribution because it carries over into this section. And even for your next learning unit, it's also going to feed into that learning unit as well. Any questions on this? Is anything that's confusing, you're not sure about? Thanks, Shakira. Okay. Thanks, Neo. Okay. I will give you some exercises to practice as well. Please work through those exercises. It's very important. Okay. It really helps you figure out whether you do understand it or whether you don't. And if you don't, then reach out to me. Also, just a reminder to complete your ICE tasks. I believe the due date is in very early May. But I'm hoping all of you completed them, right? You should have completed all of them by now. But yeah, let me check the chat. Any questions? If not, all right, thank you, people. You can drop off if you'd like. Appreciate you joining this session. Have a good night.